we'll start discussing about DC machines, right? In this class, we will see what is DC machine, right? So let us start discussing with DC machines. DC machines, DC machines. DC machines means it covers both generator and motor, right? DC generators, DC generators, and DC motors. Motors together, this generator and motor together, we can call it as a machine, DC machine. DC machine. So out of these two, DC generator and DC motor, first we will try to understand what is DC generator. DC generator. So here generator means which converts mechanical input into electrical output. Which converts mechanical input into electrical output is called a generator, right? Which converts mechanical input into electrical output, which converts mechanical input into electrical output is called generator. Is called generator. If this electrical output is DC, if electrical output is DC supply, if electrical output is DC supply, DC means direct current supply, then the generator is called DC generator. Right? And this DC generator works on Faraday's laws of electromagnetic induction principle. This DC generator works on Faraday's law of electromagnetic induction. Electromagnetic induction principle. So in order to understand how generator is producing electrical output, for that we need to understand what is Faraday's laws of electromagnetic induction, right? We need to understand Faraday's laws of electromagnetic induction. So for that, let us try to understand this Faraday's laws, right? So let me explain Faraday's law of electromagnetic induction, right? Coming to this, Faraday's law of electromagnetic induction principle. Most frequently we can call it as Faraday's law, that's it in short, right? So what this law is stating, whenever conductor means wire, is moving in time invariant magnetic field, time invariant magnetic field, time invariant magnetic field. If conductor experiences, if conductor experiences change in flux linkage, change in flux linkage, change in flux linkage, change in flux linkage, then EMF will induce in that conductor, right? So this is the statement of Faraday's law, right? Coming to the statement, this is Faraday's law of electromagnetic induction principle. So the statement is, whenever conductor is moving in time invariant magnetic field. So here time invariant magnetic field means it is a DC magnetic field, that we need to understand. Time invariant magnetic field means it is a constant magnitude magnetic field. That flux magnitude should not vary with respect to time. It should have constant magnitude. That flux should have constant magnitude. So constant magnitude flux we require means we have to give constant current. We have to give constant current, right? So constant current is possible with DC supply only. So that's why I am calling it as DC field, right? DC field, right? So in the DC field, if we are moving conductor, if that conductor experiences change in flux linkages, if conductor experience change in flux linkage, then EMF will induce in that conductor, right? So this statement we need to understand practically. This statement, right? This statement we need to understand clearly. So in order to understand this statement clearly, what I am doing here is I am taking some magnetic field system. So according to this statement, I understood that here we require conductor, and then we require time invariant magnetic field, and this conductor should be moving in nature. So this arrangement we have to do here. So for that one, what I am doing here is, let me take magnetic system like this, which is having north pole here, and here south pole, and we know flux lines flows from north pole to south pole like this. Actually, very huge number of flux lines are flowing from north pole to south pole. So in order to understand this concept clearly, I am representing very few flux lines which are flowing from north to south, and these flux lines are having direction in this way, right? Right? And this I can say time invariant magnetic field. So how time invariant magnetic field is prepared? Time invariant magnetic field is prepared by DC supply. So for that, what we require? We require iron core. Let me consider this as my iron core. On this iron core, let me put winding, right? Winding like this. I can put winding in this way. Like this, I can put winding, right? This is the winding, and here also I am putting same type of winding, right? And this winding is joined like this, right? And this winding ends I am taking here. These are the ends, right? So current direction of the winding, current flowing through the winding is in this way, right? So this is how current is flowing, and here also current is flowing in this way. So here current has to flow in this direction, means your battery connection should be, DC supply connection should be in this way. DC supply connection should be in this way. So let me consider this as positive, this as negative. I can write it as DC supply. DC supply. So this type of arrangement we can call it as electromagnet, right? Whenever current is passing through the winding, see here this winding is having some n number of turns, right? That n number of turns I have split it into two halves. Half of the turns are placed on this pole core, iron core, and remaining half of the turns I have placed on this iron core. And I have placed a number of turns in this way, right? Winding is inserted in such a way to carry current in this direction. So for this current direction, I can say flux can flow towards this way, right? If you see north pole, by using thumb rule, right? By using right hand thumb rule, see forefinger curl represent current direction and thumb represent flux direction. So if you apply this concept to this north pole core, iron core, see current is flowing from top to bottom. So in that direction I am rotating my four fingers, and while rotating four fingers in current direction, thumb is projecting direction of the flux. In this way it is projecting. So I can say flux lines are flowing in this way. And here also same way, current direction is represented in this way. Current flowing through the wire is in this way. So this represents flux direction, right? So orally I can say flux lines are flowing from north side to south side. So in this direction flux lines are flowing, and which are having constant magnitude. Here I have applied DC supply, which is having some voltage, fixed voltage. Depending upon fixed voltage and winding resistance, this winding is going to have resistance. Depending upon that resistance and applied voltage, current flowing through this term is same. So whenever current is flowing through this winding, what will happen? That winding can be act as electromagnet. It becomes as an electromagnet. Whenever it is becoming as an electromagnet, it can produce flux lines, and that direction of flux lines can be produced, identified by using right hand thumb rule. So now we understood, by giving electrical supply, by giving electrical input to coil or winding, to any coil or any winding, that winding or coil is going to be as an electromagnet. Whenever it is going to be act as an electromagnet, it can produce a flux lines, and that flux lines can be determined by using right hand thumb rule, right? So current direction can be represented with four finger curl in this way, and thumb represents flux direction. So now we have prepared a magnetic system, right? Which is called electromagnetic system, right? Electromagnetic system. So now in this electromagnetic system, we need to place a conductor. So let me take conductor here. I am placing conductor here. See, conductor I can represent with some circular symbol. Actually conductor is nothing but a wire. Wire, how it is going to be? Wire is looks like a straight line. Wire looks like a straight line. But if you draw three-dimensional view of that wire, then it will be like this. And for this one, if you look at from this end, if you look at from any one of the end, how it is going to look like? It looks like a circle. If you see from any end, that may be from this side or other side, if you see from end, it looks like a circle. So that circle I have represented here. So now I can say conductor is placed inside the magnetic field. Whenever conductor is placed inside this magnetic field, this is my conductor. Remember, this circular representation is my conductor. And whenever placing conductor inside this magnetic field, I can say that magnetic flux lines are flowing through this conductor, right? Whenever conductor is placed inside the magnetic field, by the time magnetic flux lines are flowing through the conductor. Whenever magnetic flux lines are passing through the conductor, or it is penetrating through the conductor, flux lines are penetrating through the conductor, right? So it is flowing through the conductor, it is entering into conductor, and then it is leaving. So whenever flux lines are passing through this conductor, I can say there is a flux linkage. But it is not change in flux linkage. Remember, this is very important. Whenever flux lines are passing through the conductor, then I can say conductor is having flux linkage, right? Flux lines are passing through it, so we can say it is a flux linkage. Whenever flux lines are passing through it, we can say it as flux linkage, but it is not having change in flux linkages. So in order to make in order to have change in flux linkage, what we need to do? We have to move the conductor. We have to move the conductor from one place to other place. So in order to move the conductor from one place to another place, we require mechanical input. We require mechanical input. So when you give mechanical input, that is in rotating fashion, right? So conductor can move one place to other place inside this magnetic field. Inside this magnetic field only. We should not move conductor outside this magnetic field. If you are moving outside the magnetic field, there is no concept of inducing EMF, right? So that is out of reach, right? So whenever conductor is placed inside the magnetic field, and if it is moving from one place to other place, that I am calling it as conductor is moving in magnetic field, time invariant magnetic field. If it is experiencing change in flux linkages, right? So whenever your conductor moves from one instant to other instant, what will happen? This conductor experience different amount of flux lines. So the different amount of flux lines, I can call it as there is a difference in flux linkage. Yes, there is a difference in flux linkage. I can call it as whenever a conductor is moving from one place to other place, I can say there is a change in flux linkage. There is a change in flux linkages. Whenever conductor moves from one point to other point, if this conductor is cutting the flux line, more specifically I can say if this conductor is cutting the flux lines, let me consider like this. See, this my four fingers are consider it as a flux lines, right? And if you consider this pen, I mean this ink pen as conductor, if I move this conductor in this way, conductor in this way, what will happen? This conductor cuts the flux lines. So whenever conductor cuts the flux lines, then I can say this conductor experiences change in flux linkage. So whenever this conductor experiences change in flux linkages, in that case EMF will induce. This is according to Faraday's law of electromagnetic induction. That is what the statement tells, right? All of you observe this statement carefully. See, whenever conductor, that is wire, is moving in time invariant magnetic field. See, this is the conductor. If this conductor is moving in this time invariant magnetic field, time invariant magnetic field, if this conductor is moving from one place to other place, if conductor experiences change in flux linkage, why I am calling if, why I am telling here if means sometimes if your conductor is there here, right, sometimes there is a chance to have conductor in this place, right, right. See, this is the one more position of the conductor, right, while rotating from one place to other place in this circular fashion, one instant conductor may appear here, then after some time conductor may comes to here. Whenever conductor is coming to here while rotating in circular fashion, while conductor is rotating in this circular fashion, what will happen? During this instant, that means whenever conductor is exactly under the center of the north pole or center of the south pole, what will happen? Flux lines and conductor movement is in perpendicular. See, flux lines are flowing from left side to right side, that is from north pole to south pole, that is perpendicular, and conductor is moving towards upper side, like this. Conductors are moving. So whenever it is there in this situation, I can say flux lines are flowing along with x-axis and conductor is moving along with y-axis. That means there is a perpendicular displacement. So because of this, what will happen? There is a more amount of change in flux. Or I can say there is more amount of flux cutting is there by the conductor, right? So I can say at this instant maximum amount of flux linkage is happening in by the conductor, right? But whenever conductor comes to this region, right, conductor comes to this region, by the time conductor is moving in this direction. See, conductor is moving in this direction and flux lines are also having same direction. So whenever both conductor and flux lines are having same direction, I can say both are in parallel. Whenever both are in parallel, then I can say there is no cut. There is no cutting of flux lines by the conductor. As there is no cutting of the flux by the conductor, then I can say there is no change in flux linkage. That is what I am trying to say here. That's why I have written here, if conductor experiences change in flux linkage. When conductor experiences change in flux linkage, whenever there is an inclination, whenever there is an angle between conductor movement and flux direction, right? flux direction and conductor movement, if you observe, whatever the direction, it may be towards the straight, towards the top side, or it may be flowing towards some inclination. If any angle is there, if any angle is existing between direction of flux and movement of the conductor, then what will happen? Flux linkage will exist, change in flux linkage will exist. But coming to here, see, in this region, see, flux lines are flowing from along with x-axis, that is from left side to right side, and conductor movement is also in the same direction. So whenever both are having in the same direction, I can say there is no angle, both are looking like a parallel. Whenever both are looking like a parallel, I can say angle between flux lines, I mean direction of flux lines, and conductor movement is 0. Whenever angle between direction of flux lines and conductor movement is 0, then I can say there is no flux cut. As there is no flux cut, I can say there is no change in flux linkages. There is no change in flux linkages. Therefore, I can say whenever conductor is having change in flux linkages, right? The statement here, it tells that if conductor experiences change in flux linkages, then only EMF will induce. Then only EMF will induce in that conductor. So here we need to understand that flux linkage is different. Change in flux linkage is different, right? Whenever you are keeping conductor inside that magnetic field, always conductor is going to have flux linkage. Always conductor is going to have flux linkage. But having flux linkages won't decide inducing EMF, right? If conductor is having flux linkages, there is no induced EMF in the conductor. When EMF will induce in the conductor? Whenever change in flux linkages exist. So in order to get change in flux linkages, what we require? We require conductor movement from one place to other place. While moving conductor from one place to other place, sometimes conductor movement may be perpendicular to flux lines, sometimes it may have other angle. So during that condition, what happens? Change in flux linkage will experienced by the conductor. But in this region, in this top region, in this middle region, that means in this region or in this bottom region, if you observe conductor movement, see, a top region conductor is moving in this way, flux direction also in the same direction. So it can, both are in parallel. And coming to this bottom region, see here, if you rotate in clockwise direction, for that clockwise direction in this region, conductor movement is in this way and flux direction is from left side to right side, right? So here both are in anti-parallel. In this case, both are in anti-parallel. Whenever both are in anti-parallel, again angle between flux linkage and conductor movement is 0. Whenever angle between flux direction and conductor movement is 0, then I can say there is no flux cut. If there is no flux cut, then I can say there is no change in flux linkage. So therefore, whenever there is no change in flux, linkage, then EMF induced in the conductor is 0. So from this discussion, I can say whenever conductor is under the vicinity of north pole or south pole, under the vicinity of north pole or south pole, in that case EMF will induce. Why? Because by that time conductor is experiencing change in flux linkage. But when it comes to the center region, right, I can say this is the region which is perpendicular to this flux lines, right? If for this flux lines, this is the perpendicular region. I can say this is, if I call this as polar region, let me call this as polar region. This is polar region. This is polar region. If I call this as polar region, polar axis, I can say polar axis, and perpendicular to this is interpolar axis, like this. Let me take here. This is interpolar axis. So in this interpolar axis, along with this interpolar axis, there is no change in flux linkage. Why? Because conductor and direction of field is going to be in parallel or in anti-parallel. So upper side, if you take, it is there in parallel. If you take lower side, it is in anti-parallel. So whenever we are getting parallel or anti-parallel condition, by that time angle between conductor movement and direction of flux is going to be 0. If that is 0, then there is no flux cut. If there is no flux cut, there is no change in flux linkage. As there is no change in flux linkage, then we can say there is no induced EMF, right? And in this region, I can say that means along with interpolar axis region, I can say there is no induced EMF in conductors. But when it comes to polar region, that means whenever conductors are under the vicinity of north pole or south pole, then what happens? Conductor will experience change in flux linkage, right? There is a angle between direction of flux and motion of the conductor. So because of that, what will happen? Flux linkage will change in flux linkage is experiencing by the conductor. Due to that, EMF will induce, and that induced EMF we can represent with the equation of E is equals to BLV sin theta. BLV sin theta. So here B is maximum flux density, L is active length of the conductor. This is the conductor, na? It is going to have active length, some length it is going to have, na? So that is the active length of conductor, and V is velocity, right? This is EMF, and this is flux density, maximum flux density I can say, or flux density, and this is active length of conductor, active length of conductor, and this V is velocity of the conductor, velocity of conductor, and theta is angle between conductor movement and flux direction, right? So this is about Faraday's laws of electromagnetic induction, right? I hope you understood this video. If you understood this video, please like this video and subscribe my channel and share to your friends, right? Thank you for listening.